from the factors affecting, we have seen inductive effect, anisotropic effect. There were different divisions in anisotropic effect, one with alkenes, the other alkynes, then aromatic protons. Then we have also seen van der Waals deshielding. Then next comes hydrogen bonding. Now you know that hydrogen bonding is observed in case of polar molecules. Polar molecules means there is one functional group. Out of that functional group, one atom is very electronegative, the other is electropositive. So in that group, you have one center of electron rich area and the other electron deficient area. So what happens is, it may happen that, find the pointer, why it is not getting. Okay, it may happen that one area of the molecule is, say, electron rich, is electron deficient. Now there may be the same molecule, the other molecule which is identical, which is having a positive area and a negative area, and one electronic bond which is between two molecules, intermolecular bond called hydrogen bond is forming. So what happens is, this electron rich area, the electrons are pulled by electron deficient center. So can I say the deshielding is occurring for this particular group? So if it is deshielding, you will observe downfield signal. Now the shielding and deshielding in case of cycloalkanes, it is little bit tricky. Okay, because first of all, it is no pi bond present. So electron cloud is across two atoms forming the sigma bond. It is in between those two atoms. It is occupying a relatively smaller region. So anyway, what I was talking about is this particular region between two atoms. Okay. Now what we are looking here is isolated sigma bond between two carbon atoms. Now, if such is the case, okay, if such is the case, then there is a conical substructure of deshielding area formed around every carbon. Okay. Now, I hope you can imagine that conical region. Two-dimensional, what you are looking from here now is appears to be a triangular shape, but it is a conical, जो ice cream का cone होता है वैसे. Now, in that cone, if any group or any atom is present, that group will be deshielded with respect to its magnetic field, and anything which is outside the cone will be shielded. Okay. This happens because of the movements of the electron along the axis of the bond. I will read out the points one by one. I hope you will understand it. Compared to the anisotropic effect, मतलब जो अभी हमने इसके पहले देखा डबल बॉन्ड और ट्रिपल बॉन्ड के बारे में, of circulating pi electrons, the sigma electrons of carbon single bond produce a small effect. The axis of carbon single bond is the axis of the deshielding cone. This deshielding cone I just now explained to you. The figure over here accounts for the deshielding effect of successive alkyl substituents on the proton attached to a carbon atom. So if it is a chain, you can consider that these cones are attached to one another from end to end. Thus, protons absorb downfield in the order RCH3, R2CH2 and R3CH3. What they mean to say is carbon attached to one alkyl group and three hydrogen group, three hydrogens I mean to say, then carbon attached to two alkyl groups and two hydrogens. This is secondary carbon, this is primary carbon, this is secondary carbon, and then we will have a tertiary carbon. Okay, so we are discussing about these hydrogens in case of primary, these two hydrogens in case of secondary, and this hydrogen in terms of tertiary. So they will experience most downfield effect. Let us consider, what if it is not a linear or open chain molecule? If it is a closed chain molecule like this cycloalkane with a 6-membered ring, cyclic structure, so it is cyclohexane. So the effect will be combination of those cones formed along all six sigma bonds. So overall effect will be all the bonds which are equatorial, they will lie in the de-shielding region, and all the bonds, all the hydrogens which are present axially, they will be lying in the shielding region. They will be shielded. Okay. So with this shielding, de-shielding, you may observe this schematic diagram to see in which region which functional group will give the signal in NMR spectroscopy. Okay, this is your syllabus point. Important, asked in exam several times. Solvents used in NMR. So as in any spectroscopic technique, let us see first what are the ideal characteristic of the solvents. So important characteristic for solvent should be, they should be chemically inert and magnetically isotropic. Magnetically isotropic literally means they should not interfere with the induced magnetic field within the molecule. Then it should be devoid of any hydrogen atom. Why it should be devoid of any hydrogen atom? Because if it is not devoid of, if it contains hydrogen atoms, the solvent will have its own signal which will be interfering with the sample. Then it should dissolve the sample to a reasonable extent. If it cannot dissolve the solvent to a reasonable extent, you will get very weak signals. So signals should be sufficiently strong. Examples of such solvents are carbon tetrachloride, CCl4, no hydrogen present; carbon disulfide, again CH2, no hydrogen present; then deuteriochloroform. The normal chloroform is CHCl3. In deuteriochloroform, that hydrogen is replaced by deuterium. Then hexachloroacetone. In your acetone, you have CH3COCH3. If you replace all the hydrogen with chlorine, you will get hexachloroacetone. Some other solvents that require corrections of the order 0.5 ppm or more in tau value or in delta value are pyridine, dioxane, acetonitrile, and trichloroacetonitrile. Now, in all of them except pyridine, if hydrogen is present, you are supposed to replace that with deuterium, one thing, and all these solvents are not magnetically isotropic. That's why you need to make that correction in the tau or delta value. Okay.